So, we are in second year lab of Department of Physics of IIT Kharagpur. Today, I will demonstrate the experiment on thermoelectricity and thermocouple. So, let us know about the theory of this experiment. So, this thermoelectricity, you know, this basically we tell this thermoelectric effect. So, this thermoelectric effect is the direct conversion of temperature difference to electric voltage and vice versa via a thermocouple, right. So, thermocouple, in a thermocouple you can convert, you can see the direct conversion of temperature into electric voltage. Also you can see the conversion of electric current to the temperature. Okay. So, so in thermoelectricity, you know, there are three effects. One is Seebeck effect. This is basically conversion of heat directly into the electricity. Then Peltier effect, conversion of electricity into the heating or cooling, right. And third one is Thomson effect. This is basically continuous temperature gradient when current flows in a single wire. Okay. So, in thermocouple basically it has junction of two types of wire. These two types of wire means is made of two types of metal. So, thermocouple is a device to measure temperature, and it is made of two dissimilar metals having their junctions. So, it works on the principle on the effect of Seebeck or Seebeck effect, right. So, if you take this one wire of metal A, this is another wire of metal B. So, if you have junction, this is the junction, and you have here this is another junction, this is another junction, but we just detach it to add this voltmeter using the third type of wire, but one can show that there will not be effect of this third wire. So, that effect will be nullified. Okay. So, basically two wires, one junction is there and another junction is basically in between. So, there is a via. So, now this detached, this it is detached because of including the voltmeter to measure the basically this electricity generated in this circuit. So, here basically one junction which will put a place where we want to know the temperature of that place. Okay. And other one we consider that it is in a room temperature. It is in a room temperature, so reference is room temperature. So, then we do this way. Other way one can do this, if you want to keep this reference temperature is not room temperature, in other temperature. So, generally what we do? So we make this also, these two end also junction, just connected it junction, and in between, in one of this wire we just cut it, and here using the third this part using the third wire we connect the voltmeter. Okay. So, So, so this is the thermocouple, and from this thermocouple, in this thermocouple we should have arrangement for temperature difference in between the junctions, and we should have option to measure the voltage, that is basically whatever thermo EMF is generated due to the temperature difference. So, that we have to measure. So, that option should be there also, right. So, Seebeck effect, you know the Seebeck effect, as I told this, if there is a temperature difference between the two junctions, then there will be thermo EMF, okay. There will be voltage, voltage in the generated in this circuit in the thermocouple. So, this Seebeck coefficient is defined as S equal to minus del V by del T. Okay. Del V is the voltage difference generated because of the temperature difference del T. Okay. So, this also, this Seebeck coefficient also it acts as a calibration. So, for how much temperature difference, what is the voltage generation. So, for unit, for per degree centigrade or per degree Kelvin, what is the voltage generated. So, that one can use as a calibration factor. So, Seebeck effect coefficient is basically calibration factor. So, for measuring the unknown temperature, so basically you are measuring the voltage. So, experimentally you will know the voltage, okay. So, to convert it to the temperature, so this factor will act as a calibration factor. So, whatever voltage you are getting, so this, if you divided that voltage divide by this Seebeck coefficient, that will give you the unknown temperature. Okay. So, in this experiment, whatever I will demonstrate, our aim is to find out the Seebeck coefficient, okay, or aim is to find out the calibration factor. So, this is also called calibration factor in this, for this thermocouple. Okay. So, yeah, so this negative sign is there. So, then this thus this S is defined when it will be positive, when it will be negative. So, that I have written here. So, S will be positive when the end of higher temperature will have the lower voltage. Okay. So, actually in general expression for thermo EMF and the temperature is E equal to AT plus BT square plus CT cube, etc. So, neglecting higher term, one can write E equal to AT plus BT square, okay, because this A, B, C are the basically constant, depends on the thermocouple wires. Okay. So, now this T is basically this temperature of the place where you want to measure the temperature with respect to the reference temperature. Okay. So, this T is basically Tp, temperature of that point, minus the T reference. So, this E, then I can write A of T means Tp minus T reference plus B T minus T reference. So, this also it should be Tp, okay. So, Tp minus T reference square. Okay. Now, just okay, for the time being, or this, if T reference is 0, ice temperature, if this reference junction, if we keep at ice temperature, so this is 0 degree centigrade, right. So, then this is 0, this is 0. So, then basically it is a Tp, ATP plus BTP square. So, it is the equivalent to AT plus BT square. Okay. So, E equal to AT plus BT square. So, this is your relation between the temperature and the thermo EMF. So, now A and B are unknown, it depends on thermocouple. Either, so we have to find out A and B. Okay. So, that will be the basically calibration of the thermocouple, calibration of the thermocouple. So how we can do that? So, generally reference one you put at ice temperature and this point other junction you keep at two known temperature. One can be boiling temperature of water, another can be other standard temperature. Okay. So, or people also do this, one can be this room temperature and another can be the boil temperature. Okay. So, at these two temperature you will get these two EMF. So, now basically E1 equal to A T1 plus B P T1 square. Another equation you will get E2 equal to A T2 plus B T2 square. Okay. So, now two unknown and you have two equation, if you solve it then you will get value of A and B. Okay. So, measuring the EMF at two known temperatures. One is say at room temperature, another is a boiled water temperature. Okay. So, one can find out this A and B. Okay. Then when A and B is known, then you can basically you can measure using this thermocouple, you can measure any unknown temperature. They just put there, then what will be that induced EMF, thermo EMF you will measure, and for this induced thermo EMF, what A, B already known, so what will be the temperature that you can find out. And this temperature with respect to basically is basically this ice temperature with respect to ice temperature. So, that is 0 degree centigrade. So, you will get this value that is unknown temperature that is in degree centigrade. So, you can convert it in Kelvin also. So, this is one way to do this experiment. Another way one can do the experiment. So, one junction I will keep in ice, another junction I will keep in water. Now, I will heat the water and this water temperature will change, Now, I have to use thermometer, standard thermometer or another thermocouple to know the hot water temperature. Okay. So, now what I will do? I will just at every 5 degree change of this hot water. So, what will be the EMF, thermo EMF that I will take reading. So, I will take reading of induced EMF at different temperature of hot water. Okay. So, then basically T versus E I will that data I will get. Now, if I plot that E versus this temperature T, then I will get a curve. Now, from the slope of the curve, I will be able to find out this del V, del E or del V, that same thing. Okay. Here I have written E, but here I have written V. So, but I should write here also E, right, or here I should write V. So, from the slope I will get del V by del T. Okay. So, that is the Seebeck coefficient, or that can be used as a calibration factor. If that one thing we have to check whether it is curve is linear or not. If curve is not linear, then this coefficient you have to find at different points, and you have to make chart you have to make chart using this calibration factor, you have to make chart this EMF versus temperature. So, if you have the chart for a particular thermocouple, then for any unknown temperature, so you will get the thermo EMF, and for corresponding thermo EMF, what is the temperature, from that chart one can also find out. Okay. So let me show the experiment, and how to do that I will just show you here. So here this is our experimental setup for this thermoelectricity and thermocouple. So you see, this is a thermocouple. So thermocouple means two dissimilar metals. So this is one type of metal and this is another type of metal. Okay. So these two dissimilar metal, it has one junction here and it has another junction here. Okay. So now just one wire, just I cut it to just add this voltmeter, because I have to measure the induced thermo EMF. I have to measure thermo EMF. So this is the microvoltmeter. So this reading is coming in microvoltmeter. So this I have put I have put in 10 millivolts. So in millivolt range. So it's basically whatever reading it is showing, that is in millivolt. Okay. So basically here now is negative reading, etc. Just forget it. So now these two both end are at room temperature, right? So that's why this reading is almost 0. Reading is almost 0. So this is the thermocouple. This copper constantine, one wire is copper and another wire is constantine. I will tell you about, I think I should tell slightly more about this different type of thermocouple people use in their lab. So I have that chart. I will tell you what are the types of thermocouple. So types of thermocouple, here their different name is given, J type, K type, E type, T type, R type, S type. So this name are basically depending on the combination of the two types of wire. So J type thermocouple we tell when these two wires, one wire is iron, another wire is constantine. Okay. So constantine means 45% nickel and 55% copper alloy. Okay. So constantine. So this can be one type of. So people found the combination of the two types of wire. They have chosen the material in such a way so that the Seebeck coefficient should be high. Okay. And also for different range of temperature, this thermocouple, different types of thermocouple is used. Okay. So here also I have given, so this type of thermocouple is used for this range of temperature, for measuring 50 to 750 degrees centigrade. So another type of thermocouple, chromel alumel, very popular thermocouple, chromel alumel. So chromel means 90% nickel and 10% chromium, and alumel means 95% nickel, 2% manganese, 1% silicon, 2% aluminum. These are alloy. Okay. So this combination is used for measuring the temperature in this range 50 to 1250 degrees centigrade. Okay. So similarly, chromel constantine, copper constantine. So whatever I told copper constantine, so this thermocouple is our whatever I was showing, that is copper constantine. So this this name is given, this T type thermometer. So R type thermometer, S type thermometer. So R type, S type, these thermometers are used for measuring higher temperature, and this thermometer is used basically this T type thermometer, this measuring for lower temperature. Okay. So, these are the different types of thermometer. So, copper constantine, again constantine, as I told, this constantine means 45% nickel and 55% copper. So, that is the alloy. So, this thermometer we are using in our lab. So, I was showing you. So, this is the thermocouple of copper constantine. So, two junction, one is this junction and another is the other one, this one. So, and just here just we cut it here, one of this wire of the thermocouple, and we add this third type of wire to connect the voltmeter. Okay. So, this addition of this third type of metal in this thermocouple, this one can show that this this effect of this third type of wire or metal is nullified. Theoretically, one can show it will not affect this the theory of this thermocouple. So, it is the basically is nullified. Okay. So, but condition is that these two end has to be in the same temperature. Okay. So, now here I have, you see, ice bath, I have ice bath, and here I have this arrangement for heating the water, So, now I started heating the water, and now water is boiled. So, what we will do? Which method we will follow? Method will follow just this one will change the temperature of this hot water, and this one end basically will keep in ice, one end of this junction, one junction will keep in ice, another junction will keep in. You see, just note here, it is now it is showing this reading 0.73. So, because this reading is for the temperature difference, this junction is at room temperature. Now, room temperature it is around 23, okay. So, it is 0. So, this temperature difference is 23, and for that what is the thermo EMF voltage, that is 0.71. Okay. So, interestingly, I can show you that if I put this both end at the same temperature, then what happens? If I put this two end at same temperature, it should be 0. It should be 0, right? It should be 0. This reading should be 0. Yes, it's almost 0. It's almost 0, right? Okay. So, these two junction is at same temperature. So, there should not be any thermo EMF, it should be 0, and that is what it is 0. It is going towards negative, any slight fluctuation. So, now one junction is at ice temperature, another junction I will put in hot water. I am putting in hot water. So, it is really hot now, its temperature is I will tell you what is the temperature. So, if I put, yes, so I put in hot water. So, now just you check this reading here. So, one junction is at ice, another junction is at hot water. Now, I have to just wait for some time to get this, to stabilize it, to stabilize the temperature of this hot junction. Now, it seems it is stabilized. So, I have to take this reading. It is varying 3.72 to 3.71. 2, yes. So, I can take this reading 3.71. Okay. So, if I wish, then I can start to take reading at this temperature. So, what is the temperature of this hot water? Now, I can use this thermometer, I can use this thermometer, I can use this thermometer. So, this thermometer can measure up to 110 degree centigrade. So, this I will put in hot water, and then what is the temperature I can take reading from here. But I will not do that, we have another arrangement, more accurate arrangement. So, here you see we have used another thermocouple, we have used, this is a commercially available thermocouple. So, basically this here you can see this commercially available another thermocouple I have used, and this end is in the hot water. So, this meter is basically calibrated one, this calibration is done by the company. So, because of this in this thermocouple reference is room temperature and one end is the temperature where you want to measure. So, at that place this another junction. So, this meter here it is showing the temperature directly because this thermocouple is calibrated by the company, and that Seebeck coefficient or this calibration factor is multiplied with the EMF. So, it is the electronically inside. So, it gives the basically then display the temperature. Okay. It display the temperature. Now, what we will do? So, now at different temperature of this hot water I will take reading. I will take reading of this voltage. So, now it is if already this is hot. So, basically we should start say around 60 degree centigrade or 70 degree centigrade. Okay. And then you vary the temperature, you will heat the water, and the temperature of this water will change, will increase. So, for each 5 degree temperature change, what is this value, that I will note down. Okay. Now, it is 87. So, for that 3.5 millivolt, 87. So, these are the temperature. Now, if I think I can just I think heater is on now, right. Heater is on. Now, I will increase the temperature, or other way I can do, I can just reduce the temperature just putting cold water, reduce the water, just if I put cold water, slightly cold water, then I can reduce the temperature. It is changing the temperature, you know, it is okay. So, if I start this, what is happening? So, this is fluctuating, or is heater is started to heat. Oh, this is heating very fast. So, slightly more water, cold water I can give, because I think I should start from 50 degree centigrade. And then it may be around 50. Okay. So, slightly hot water I can take out, and then you put more cold water. You put more cold water to reduce the, okay. So it's still, it's a 63, 61, 59, 58. Okay. So you have to choose temperature of beginning temperature, okay, and then for that temperature, but it's fluctuating, its temperature is reading is fluctuating. So I have to take average reading, or one can use this thermometer also. Anyway, so it should stabilize. So temperature is around 60 degree. So for 60 degree, what is the voltage? You have to take reading. Now I will start heating. And then I will take reading at 65, then 70 degree centigrade. What is this value? Then 75, 80, 85, 90, 95, as long as it goes. I think around up to 90 is also fine. So each 5 degree step I will take reading. Okay. So within this range of temperature 60 to 90, that I will plot this voltage, this whatever reading here we are getting versus this temperature. And then for this range of temperature, I may get the state line or may not get. If I get state line, then this Seebeck coefficient is constant, okay, throughout this range of temperature. So Seebeck coefficient, it will depend on the range of the temperature. It may not valid for the full range of temperature. So that's why. So in which range you want to calibrate this thermocouple? So you have to do this experiment up to that temperature range, and you have to see whether it is linear or not linear. Generally it is not linear, but in a particular, so that depends on thermocouple also. Okay. So in a particular range it may be linear, and then we tell that okay, this thermocouple will work up to in this range, or it may happen that there are so it's changing. So there are different range, and for different range there will be different Seebeck coefficient, means calibration factor, that one has to take care. And if it is really non-linear, then for each point you should have the you will have the different Seebeck coefficient, and in that case calibration just one calibration factor is not enough. So you need this curve, either this graph method or this chart method. So for that thermocouple you have to prepare a chart for different temperature, what will be the EMF, or for different EMF what is the value of the temperature, or it can be, if you plot it, so from graph also one can find out what will be the temperature for a particular thermo EMF. Okay. So it depends on thermocouple. So here say you are trying to find out the Seebeck coefficient for a particular range of temperature. Here I started from 60. Okay. So 60 to up to 90 I will do the experiment, say, and then I can find out the Seebeck coefficient only for this range, and I cannot claim this Seebeck coefficient will remain same above 90 degree centigrade or below 60 degree centigrade. So it depends on your experiment and your claim also. So these things one should write in discussion. Okay. So here now it is 65 degree centigrade. So this voltage I have to note down, it is 2.6. Okay. It is 2.6. Now I will again wait, and when this temperature will be 70, then I will note down this one, this thermo EMF. So this way you should make table, this temperature of hot bath versus the thermo EMF, and reference temperature is basically ice temperature, that is 0. So this is the experiment, and from that from the plotting of the graph one can find out the Seebeck coefficient. So del V by del T. So now if it is non-linear, so then we tell dV by dt. Okay. So dV by dt means the differential form. So it will vary at each and every temperature or each and every voltage. So here, okay, it is not 78. So it is increasing from 2.6 to it is going to 2.72. Okay. So this way just you have to continue the reading and do the rest of the things, including the error calculation, and you have to write this, write the answer. Okay. So if you find out, so after finding out this Seebeck coefficient or calibration factor, if you, so generally we tell to measure the unknown temperature. So then you hot junction you have to put in unknown temperature, and but this reference junction has to be in ice. So then find out this value of this. It's 70. So it's a 2.8. You have to note down 2.8. Okay. So for unknown temperature, so hot junction, now you have to put in that unknown place where you want to measure the temperature, and then just you have to note down this one, and then from graph or from chart or from, if it is linear, from calibration factor or that is called Seebeck coefficient, you can just convert to the temperature. Okay. So this is very simple experiment, but is technologically very important experiment, because this thermocouple is, you see, this mercury thermometer is used in very few places. It can measure the temperature from ice temperature to say boiled water temperature. Okay. So 0 to 100 in this range you can use mercury temperature, this mercury thermometer. But when you want to measure say above 100 degrees centigrade, so 400, 500, 600, 1200, 1500, 2000 degrees centigrade, 3000 degrees centigrade, what you will use? So this thermocouple is used for the broader range of the temperature. Okay. So that's why different types of thermocouples are there, means different combinations of wires, as I showed you, J type, K type, T type. Okay. So it's a very very useful thermometer for the lab, for the industry, and advantage of this one is that this directly you are converting temperature into the electrical signal, and for interfacing, okay, of any instrument, so depending on the temperature. Okay. So this thermocouple is very useful, because mercury thermometer when you will use, then it is not, you are just observing the reading, right? You are not converting to the electrical signal. Okay. So these are non-electrical, and for interfacing you need to either temperature or pressure or force, you need to convert into the electrical signal. So that's what this basically sensor, transducer. Okay. So that has come up how to convert the convert the non-electrical parameter into electrical parameter in terms of electrical parameter. So, here thermocouple is directly it is coupled with this conversion of the non-electrical temperature to the electrical thermo EMF. Okay. So, that is why this thermocouple is very useful for industry, for lab, and and also another advantage is that this thermocouple is used for the broader range of the temperature. So, it seems is a very versatile thermometer, and so thus this principle of this thermocouple for measuring temperature today we demonstrated, and this very you should understand it clearly. And it is very useful for the common use in the laboratory or in our industries. Okay. So, so it is a temperature increasing and this also increasing, one should take the reading, and important is that how the arrangement is made, and what is the significance of each and every tools, okay, that one has to understand, and you should not forget to note down the least count of each instrument whatever you are using, because you will need to calculate the error on this measurement. Okay. So, yeah, so I think I will stop here. Thank you.